is here as a JPL staff member who's working in machine learning for computer vision. And it's pretty amazing, again, that we're going to have him here today for the technical lecture and to be around both today and tomorrow to help you all out with your build. Since we're working computer vision this week, I'm sure you'll all find his expertise and guidance very valuable in the work that you're doing. I want to remind everybody about the etiquette rules, so laptops, phones, closed, off, so we can give our full and undivided attention to our guest today. And I think we can get started. Everybody's here, so we'll just jump right in and turn it over to Sheryansh. Thanks.
Hello, check. Is that good? Hey guys, my name is Sheryansh, as Ken introduced. I'm excited to be here. It's not long ago, I was on the other side, just a year ago. So a bit of background, I was born and brought up in India. I came to the US and did my master's here at Carnegie Mellon University. I did a master's in robotics where my focus was mostly on computer vision and machine learning applied to real world robotics. I've been playing around mostly a lot with robots that move on the ground as well as aerial robots. So I'm trying to apply computer vision techniques to them. I graduated last summer, as I said, and then I joined JPL. And since then, I've been working at JPL mostly on computer vision and autonomy for Mars exploration. As you see, this is the campus for JPL located in LA. It's a beautiful campus out there. And before starting on the actual lecture, I would just give you a bit of introduction of some of the cool work we did. I think my colleague Kyle was here last week to talk with you guys, and he gave a brief introduction as a broad, high level of what we do. But this is more focused on some of the more robotics work that we have. A lot of the work that we do is mostly for NASA, and a lot of that deals with actual Mars, and not just Mars exploration, but also outer planet exploration. So if you see on the right there, we have an underground robot, basically, that we are designing for Europa. So the idea for that is that we want to go on underground oceans on Europa, and how can we build robots that can go and explore that? And again, all of that needs to be autonomous because those are several light years away, and we do not have a way to do real-time communication with them. So once we send them, it'll be really hard to have any form of communication to control them by hand. So we've been doing some tests in Alaska with that, where we go down to Alaska and we send this robot inside below ice sheets so that it can go and explore and map the environment there. One interesting project that I've been partly worked with is the Mars helicopter. So NASA is planning to send a quadcopter, which is not really a quadcopter, but a single rotor helicopter that we'll be sending along with the next Mars rover to allow aerial navigation and ground robot aerial navigation. Again, unlike the ground rover that we have right now, which is partially autonomous, and we do give it some form of directions on how to get to some point. This needs to be pretty autonomous because the time in which the autonomous flight happens is less than the time of communication between here to Mars. Then again, we don't just work for outer planet exploration, but we're also doing a lot of stuff here for Earth science. And I'm not sure if Kyle talked to you about RoboSimian. He's the guy who's been mostly working with RoboSimian, and we've been developing that robot as part of the DARPA Robotics Challenge initially. But now we've been looking into how can we use a human-like, or more like a spider, monkey-like robot for replacing humans as well as astronauts as well as other, and actually seeing how can we deploy it into real-time, real missions as opposed to a research platform. So at JPL, we do all kinds of robots that go underground, under caves, underwater, on the ground, sea, as well as aerial. And we mostly deal with autonomous systems. So that's the perfect place for something like computer vision, what you guys are learning here, because if the robots need to be autonomous, they have to have a good sense of perception and learning and evolve over time. And that's what we're doing. And I'll be happy to talk to you guys about any of the work that you guys find, if you guys find interesting. So I'll be here till tomorrow. So I would love interaction and Also, I was talking to Ken about this. We are open to interns. Also, we are always looking for highly talented people, even at the high school level, who can come and help us with all the work that we are doing. So if you're interested in space and robotics, JPL is probably one of the only places in the world that you can find where you can do a bit of both. So write to me if you guys are interested in that. OK, so starting with the lecture now. Basically, I've been told that you guys had a brief introduction of computer vision already. So I would not go into the fundamentals of computer vision, but in this lecture, I would try to cover computer vision from a point of view which is of more high-level perception and try to motivate you into see why machine learning and artificial intelligence is required to take computer vision to the next level, and that's where the focus of the community right now is. And especially with the coursework that you guys have with the robot car, that's another. I'll try to basically motivate how some of the machine learning techniques can be helpful in places where the other perception or basic computer vision fundamentals that you have studied may not work. So let's start with some the basic motivation first. What is the goal of computer vision? As I would like to state it, it would be we want to design systems, in this case a robocar, or probably some, like the other course or UAV, would be something that can understand from visual data. So what do we mean when we say understand? What does it mean to say a system understands? So that takes us to how the vision story actually began with some of the early work on computer vision. And David Marr, one of the pioneers of computer vision, stated it as basically we would want to know what and where by just looking at an image or looking at where the robot is. But that creates a problem because it's not very certain and it's not a direct answer to that. If you look at this image here of a living room, this can have multiple interpretations if we ask questions which are not direct. For example, if we look at a particular pixel in the image and we ask a question, what is it or where is it? How do you define it? There are multiple ways to define it. One would be the machine level way, where the machine would say this is at a particular X or Y position in the image and it has a particular measurement. And then the other would be, if I ask you guys what would be, that you would give me a more semantic answer about it. That would be, it looks like a flat sittable area. Or you would define it in human language. And this is something that needs to be captured and that separate out two major parts of computer vision. And that needs to be identified clearly, because is it just something about semantic labeling, or is it about a fact or how we define things, or is there some more fundamental difference on how we actually approach problems or how we are tackling with this? And in general, the community has this divided into two areas of computer vision. One would be measurement and one would be perception. Measurement would be when you use computer vision technologies to measure something which is more factual. For example, how far is somebody sitting from me? That would be a measurement. Whereas, how does he look, or what is it? What is that, a chair? That would be something perception and a higher level understanding of it. A really nice example that I had studied and motivated me was to look at this. So if I ask you guys, has any of you seen this already? Yeah. OK, forget it then. OK, I guess this was covered by somebody earlier in this. So I guess you know this part then, that the difference was that this has the same, and this kind of illusion is all over around us. Like you would have on social media, you can every day see things on optical illusion, basically like that fools our mind. Last year itself, I remember this viral thing about the two dress colors having like black or gold, and then that went viral, and this optical illusion thing just. So this is something that our brain is really good at. So this captures the difference between what measurement, where both of the colors actually have the same measurement, but the human brain perceives it in a different way. And the thing that needs to be understood here is it's not necessarily always the exact measurement that matters, but also the context of the environment. In everything around the world, like things that we define are often defined by the context around it. Several symbols that we know completely change in meaning if if we change the context around it. And that does need to, and the reason why this happens here, I guess you guys already know, is the difference between black and white. The contrast between that it looks like, and our human brain is so trained to look at it in a particular way, it just gets fooled into understanding that they are of different colors. This is another example. I'm not sure if you guys have already seen this, probably, but if you see the two red lines here, the human brain would very easily distinguish that the wall is much taller than the window. But actually, if you put two parallel lines through it, you would see in the image they actually have the same dimension. So if you use a simple computer vision method that just basically would measure the length of the line to estimate how far it is, this would not give you a good perception about it. And the reason for that is that we are missing a very fundamental thing about how our human eye works versus this, that we are or rather how the human world is and how we capture or look at images, is that we are missing a complete dimension here. This is everything mapped from 3-dimensional to 2-dimensional. And that loss of dimensionality actually creates these illusion effects. By the way, if you guys have any questions, feel free to just interrupt me. So summarizing that, basically measurement is capturing some of the physical quantities that we have around us, whereas perception, how I would at least define it, would be a more high-level representation of how we understand the world around us and make sense of the visual data. And this lecture would concentrate more on the perception part of it. There's been a lot of previous work. A lot of the computer vision in the earlier decades throughout from its start was mostly focused on measurement because that's where the major need was. And we had, even at NASA, we had things that we built that was used. We put a stereo camera on the Mars rover, and that was mostly used to basically just map out the environment while the robot is moving. So how far the rock is, or how big the rock is, so that once we have that measurement, we can plan a trajectory around it to avoid that obstacle. Then there was a lot of work that was on reconstructing. Street View, Google Maps, these were all in ways products of some of the work that computer vision happened, where we were trying to reconstruct buildings and the whole cities around us. But this is mostly that deals with measurement. But what we care about right now, at least for the sake of this lecture, is more about perceptual understanding. And why we do that is so that we can have a more human-robot collaboration in certain ways. We don't want robots to be things that work independently and just use as tools, but something that is soon becoming part of our own community, and we want to interact with them and talk with them. Just like we talk to Alexa, and if Alexa talks in machine language, none of us would be able to talk to them. But the only reason those things are becoming popular is because we're bridging the gap between how robots work and how humans think they work. So what do humans really care about? So when you look at this image that we're using as a standard to explain some of the parts of this lecture is, you can ask several questions to describe this image. The moment you look at one single image, you already have so much, the human brain is so well trained that you have so much understanding of it already. So if you ask a question about what is the image depicting, so that would fall under the problem within computer vision of image recognition or scene understanding. So most of us would be able to easily define this as a living room. Then we can change the question about what is this particular object in front of us? And then the problem that comes down is object detection. And then the answer doesn't need to be a single class anymore. So what I want you to identify here is how the output also changes and how they are all of them are in a way the same measurement, but they are different high-level understanding. And this mapping between going from measurement to high-level understanding is something that falls within mid-level and high-level computer vision. And that's where machine learning brings a lot of focus to. Another problem here is of segmentation. So in the last question, in the last image, we asked the question, what is it? In this image, we are asking the question, where is it? So if I tell you that there is a couch in the image, can you label me exactly where this is? So trying to connect it with the final project that you guys are doing with building the robot car, you can ask the question, where is the road in the image. So if you guys know where the road is, you can able to find out basically where to move or where to define the path of the thing. This could be thought of in terms of finding the lane in which the robot car moves. And these are some of the exact things that run on the self-driving cars that Google or Uber runs these days. Basically, they are running the basic versions of these technologies in real time to find their way and navigate autonomously. Then there's a very interesting thing that humans do really well, but we're still having trouble with, is complete 3D understanding of it. When you look at this image, humans have such a nice perceptual understanding with all our experience that we can clearly see that there are these different walls. And we have idea about the geometry of the whole image, and we can even reason about a missing dimensionality in the image. This is a two-dimensional image, yet we have a very good three-dimensional idea of what is happening in the image. For example, what is the size of the different objects? This kind of thing is not still very easily done by robots, and this is where a lot of the current focus of the work is, in how to get good 3D scene understanding of the image, or even functional understanding. We are now at a phase where computer vision is starting to push, and now we are going into things which are even beyond. We're not even asking simply facts from the thing, from our algorithm, but we want it to actually tell us even more smarter things, like if I look at an image, if I enter into a room, the robot, if a robot, for example, is entering into a room, can a robot figure out for itself where to sit or where to move? And this would apply to, or if it's a Roomba robot, for example, then where can it move? You don't want it to be moving somewhere on a sofa, on top of a sofa. If you want to move it just on the floor, then it should be able to reason about itself that it's moving on that. Just yesterday, I was reading an article where one of the robots suicided itself by falling into water itself. And the idea was it just did not have a good understanding of the materials. So if this kind of a robot, if we can give it an intelligence where it can reason about the scene around it and the materials around it, then it can do a more higher level reasoning that humans can very easily do. Okay, so moving quickly away from the last basically motivation on this was activity recognition. And this is especially interesting because this is one of the hardest problems right now in computer vision. And this is one of the motivation I use, at least, for bringing machine learning, and for the fact that it's very hard to just looking at the image for a computer to tell what is it's trying to do. But humans have a very good idea of forecasting or even predicting what they can do. And this is very important, especially, so again, going back to autonomous cars. While we are driving, especially in cities like LA where I drive, it's really difficult to predict what the other driver is going to do. And if you cannot do that, you're in a bad situation. But humans need to not just try to basically interpret the visual understanding of the facts around us, but try to forecast them ahead. And this is very critical for self-driving cars also, because they need to be reliably predict the behavior of what other cars are doing based on what they can see currently. So the next I would try to motivate is, why are these problems hard now? I'm not sure on what detail you guys have studied computer vision so far, but as far as if you guys have at least gone through the basic fundamentals, the image processing fundamentals are designed to mostly interpret or do process computer vision on some of the standard data sets or some of the techniques that are very structured in structured environments. But when you start to take it out into real world, and when you start putting computer vision technologies into an actual product, you need to start dealing with all kinds of input data. And that is where computer vision starts to fall rapidly. And some of the points where it starts to is like, if you have basically designed a computer vision algorithm that looks at a straight image, and then you have an image which is sideways, can you still predict that it's a face? And why this is useful for some of the things we're trying to study here is the reason why we had the Tesla car accident, the only fatal car accident earlier this year. So the Tesla car has been designed to operate in highways and in particular environments, but it encountered a very rare situation where the truck was standing a white rock which was standing horizontally across the runway. It's one of those edge cases or rare cases which you would never expect or design your algorithm to be. So if you have a very model-based design where you're designing your algorithm based on certain assumptions that you expect to encounter, then you will start falling into certain cases which you haven't seen. And then those could lead to pretty critical errors. And you don't want this. And this is only possible if you actually if you design these algorithms to learn like humans do. We humans, because the reason why we humans can do this is because we have seen these things before. Another thing that most computer vision things need to deal with is like shadows. If, for example, you're designing your race car to work outside in the sun, inside in the room, and then you take it outside and you start getting shadows, everything you designed will fail. So how do you take these things into account and design for robustness? Occlusion. So if you give this to a computer vision algorithm right now and ask if there is a horse, it would say no, because there's no complete horse right now in the picture. But humans can very easily say there's a horse in this. This idea about occlusions, about scale, deformation, how dynamic obstacles around us work. So right now with your robot cars, you'd probably have static obstacles, but at the same time, you can have walking humans. So how do you change to design your algorithms to adapt to different ways in which a human or any object can be found? Clutter. We can design algorithms for simple backgrounds, but like if something very cluttered like this is there, can you still identify things in that? This is a good example that I like to use in a way. Okay, let's say you design an object detection class, and you basically you design your algorithm, okay, this is how a chair looks. Next time you get the picture of a chair, you should be able to predict a chair. But how do you really define a chair, to be honest? I mean, all of this a human will define as a chair. There's no fundamental definition that we have of a chair. So how do you, if humans also don't know the real answer to that, how do you actually define it for an algorithm? So this is something that's captured by inter and intra-class variation, that when we say that it needs to, somehow we need to capture this, a sense of a chair is something that we can go and sit on. And if it can find a flat area or something like that where a robot or a human can go sit on, that's probably a chair. But this is something, if I tell you to write a mathematical equation of something which you can sit on, that will be very hard to do. And so the takeaway from the last few slides that I tried to show you was basically that it's very hard to actually model the complex behavior of how human understanding and high-level understanding and perception works. 2D to 3D imaging. So going from, how do we solve it actually? So I've tried to tell you that there is a lot of problems that we have right now, but how do we try to solve it? The solution for that is how humans do it. We use a lot of data. Humans see so much images over several billions of images already as a kid by the time they are 5 to 10 years old. And they've been learning constantly, and the human brain has amazing capacity to learn all this. But even if even millions of data points right now to gather is extremely difficult for any computer system. But it's still better than a model-based system. Like if you're actually designing a system to deal with particular cases, you can only list certain number. But if you have millions of data, just by looking at the data, you can train a system to learn it, and that's where machine learning comes into. I'd just like to poll, how many of you have any idea about machine learning or have heard about it at least, or worked? How many have actually worked with it or tried to study it? Okay. Okay, so, but you guys at least know about it in a sense, that what machine learning is. And that's great, because I'm trying to basically just give a high-level idea about what machine learning is and some 2 or 3 of the most fundamental algorithms in a simple way and how they can be applied to computer vision technologies, so that you guys can go out and study that. So what will we do with data? If we have a lot of data, how can we turn that into something that we've been learning about model-based design right now? So basically, once we have a lot of data, what humans do, if we see, is build knowledge bases. For example, this looks like a chair. We have a particular model about all possible chairs that we have seen throughout. And some may be more explicit than the others, but we have some idea what the chair looks like. And that is something we call an observation model. We have some priors about the world. For example, we know that the gravity is downwards. We don't have chairs upside down hanging from the roof. So there are certain priors that we can assume that will mostly always be true unless you go to space. And then the third part about it is how do you define the mathematical models for them? So you have the data, you have certain knowledge about the world, but how do you connect the dots and you actually go from what you see to what you want to understand from that? And that is exactly what machine learning is. I would define machine learning to be a science that basically tries to get meaningful statistics out of all the data that you have seen. So for example, you guys all have emails and you have your spam filter on that. That's the most basic use of machine learning. Every time you get an email, you have your Gmail or something, it has a filter that's been trained, that's been learned using machine learning to predict whether it's a spam or it's not a spam. So every time you actually go and mark spam on your folder, spam on a particular email, your system learns again, and it's trying to adapt to what it's seeing and what it's not. And this is how we keep evolving to new attacks. And for images, that would be similar to based on the content. So for example, if I just give you the left image here, you wouldn't be able to say what is in it. If I start to give you the middle one, you probably would have some idea that it's an animal. But unless I give you the full right image, you wouldn't have. And this is something that I talked about earlier about capturing context and having the knowledge. So if we see enough of the data, this itself would be in a way able to train a machine learning system in a way that if we look at the left image, we predict it's not. So, and can we have a system, can we design a system to learn this simple behavior is the goal of today. And then this could be extended to basically other type of problems that we discussed earlier in what are the different types of animals. In the last one, it was a classification problem where it's basically, do you have a cat or not? It's more like a binary problem. But this is more about a multi-class problem where you want to classify how many images are there in the picture. So in this lecture, we'll basically take a few baby steps into understanding what machine learning is and how some of the simple techniques have evolved. And I'll teach you basically some of the fundamental techniques on applying those to computer vision systems. And hopefully you guys can use those in your robot car project to actually making it better. So trying to now go into some of the statistical understanding, statistical view of vision. So basically, computer vision, as at least I hope I would have convinced you by now, is not something which is an exact science. It's always stochastic, and problems have solutions, but they may have more than one solution. And so there's always an inherent probability associated with everything. Is it okay to assume you guys have at least a basic understanding of probabilities? Okay. So in the most simple way, we can define every computer vision problem statement into the bottom equation here, where it's a probability of something given an image. And that something can be different problems, like if it's a classification problem, we can basically say, is there a car in the image? Then that becomes a classification problem. That is the probability of having a car in the image greater than the probability of not having the car in the image. And so this could be defined into what the probability of where the car. So if you want to define where the car is, then it would change based on each pixel. So you would define probabilities for each of the pixels, and then you would tell whether this pixel belongs to the car or not. And that is how you would segment the car out of it. So how do you estimate basically this probability for something? And that something, the output is something we'll define as y, and the input would be defined as x. There are three different types of learning in a broader sense that we define right now. And those are supervised, unsupervised, and semi-supervised learning. Have any of you heard of this before? Okay. Can anybody give me an idea of what supervised is? One of them who know? Speak.
Supervised learning is when you give your like a training set, so it's working off of some like a set of data. Whereas unsupervised learning, it's when you don't have that training set. It just it's sort of like in data clustering, like K-means algorithm or something that would be like unsupervised learning. So it's basically segmenting data based on like, nearest neighbors, and like it's an algorithm based, but you don't have like a training data set input.
Exactly. I think that she captured it pretty well, and I think that is what the definition is, and we would be going into that more in details. So before we actually jump into the different types of machine learning, the different class of machine learning algorithms, there's some background notations that I want to be clear about. So those are in terms of the data and the labels that we just talked about. And in the machine learning context, you call data as features because you never really work directly with images, but you extract certain features out of this. Have you guys studied any feature representations earlier in the computer vision class? Can anybody tell me what all? Or have you guys? Yes, please.
A cone.
Sorry?
It's like recognize a cone.
Recognize a cone. Were you identifying it out of edges or counters?
Yeah, we're doing it on like a camera, so like we do it based on like the color it is, so the fact that it's orange.
Okay. Yeah, so that is one of the features. So for example, there is no hard definition of what a feature is. It really depends on what application and what task or what context you put it in. So for example, for a cone, it might be enough to use just a color. So then color is your feature. So what you would do is basically represent each pixel with the color value it has. Sometimes color is not enough, and probably representing something just by the pixel itself may not be enough, and you want to see the surroundings around it. So what you would do is use a color histogram. So you would see what's the frequency of the colors in a particular area and use that. Then there are other feature representations that you would, if you go study more about computer vision at some point, would be where you have features like sift and hawk that capture more of the gradients and scale. And so what you do is if you pass your image and you extract features out of it. So if you look at the image here, basically, not every pixel in this has a discriminating feature. So all the portion of the sky, which is white, if I just give you that, none of you would be able to tell me which is which, because all of them look the same. So what we're really looking for when we say features is something that gives us a good identity about it. So some of that could be corners, for example, the top corner of the building, or a particular orientation of the building, or the red color of the car. Things that differentiate itself from the other parts of the image is something that can be good features. So there's been a lot of work on good feature representations, and if you guys are working with Python and ROS, all of them already have inbuilt feature representations in them. So if you guys need to use that, you guys don't need to actually implement it ground up, but you can go and try to have a feature extraction run on your image, and it would give you a good set of features already. And that is something we'll be using as our input to algorithm, because you don't want to give it like a 1 megapixel image is already 1,000 by 1,000, 1 million data points inside. And you don't want to be giving it so many, because then your algorithm computationally grows very large. So you want to extract really the best features that you have in the image and use to process that. But as I said, like it could be anything. If you want, you can put in all the pixels, and then that becomes your feature. Or you extract a subset and discriminate, and you create descriptors for that. You don't just extract the pixels, but you can also find the gradients around it and define every pixel by the gradients around it, and that becomes its descriptor. But not deviating too much, that basically you have an image, and from that you extract certain features out of that. And then you have, continuing on the representation actually. So basically, yeah. So you can let us represent the input image as a set of features, and that could be M features. Let's say you extracted, always you extract M features out of your image, and from that you have a given set of N such images. So you create a whole database of data points that you have. And corresponding to each data point, you have features. For example, for every email that you have, your features could be basically your every word, and your corresponding label could be whether it's a spam or not a spam. So then you have your input and output, and collecting a lot of such input and output data, you can basically train a system. But it doesn't need to be just some output. Your output needs to also have associations to it, whether it is a positive output or a negative output. So for example, for the task that we talked about, where it was about image classification, whether there is a cat or not in the image, you would give your system a lot of examples on whether there is a cat. And if the training data has actually cat, then your label would be labeled as +1, whereas negative would be labeled as -1. So basically collecting a lot of such data points, you create your data set, which would be tuples of X and Y. And you feed these basically to your algorithm. And next we'll basically try to study how these features and labels transform into some of the, how you design algorithms to use these features and labels to actually learn a system. So this would be like a two-dimensional representation for a problem like, can we give loans? So this is not vision, but like it's still machine. This is introduction. This is basics of machine learning, and it would be, let's say you have a problem where you're trying to decide whether or not to give a loan to a student or somebody. Then two of the dimensions on which you can analyze would be your income and your savings. If a guy has enough income and enough savings, then you would probably give him loan, and those would be the data points that you have there. So let's say there were 5 people who the bank decided to give a loan, and they had enough income and enough savings. And these were the 5 people that the bank decided to not give loan. So how do you actually now, if you now get a new point, let's say a new person comes in who is somewhere in between these two, how do you make an algorithm decide whether he falls into the green category or he falls into the red category? And that is basically the definition of how a machine learning system would be designed. So there are 3 ways, as she mentioned, basically supervised, unsupervised, and then there is something called a semi-supervised that falls between them. So for supervised learning, what we would do is have a set of training data, and using that input, you would also, for each of those training data points, you would have a corresponding labels. So you would, for the object detection class where we were trying to basically say cat or no cat, we would collect, let's say, 1 million images, which some of them have cat and some of them not have cat. And you would form your X and Y tuples based on that. And using that, if you train a classifier to predict, that would be supervised learning. But let's say you had 1 million images, but you did not have anybody to actually label it for you that, okay, which one has a cat or not a cat. Or you come across a new problem which you have not seen before. For a problem like anomaly detection, how do you even define labels when you don't even know what the labels would be? So let's say you have a UFO that you see. You don't even know what a UFO looks like. So how do you actually go about telling or training a system that is a UFO or not? So that is something that would fall into the class of unsupervised learning. But most of the algorithms that you would see out there right now would fall into the category of supervised learning. And the reason for that is that we have a lot of subjective data out there that we can use to train right now. So once we have data, what do you do with that? Let's say you have a mathematical model, mathematical equation, so some polynomial with certain coefficients. Then you represent it as f. Then your goal basically is to learn those coefficients of x. So then your inference model, the final model that you're learning that will predict whether it's an email or is spam or not, whether there's a cat in the image or not, let's define all of that as f. And if the output of that, if the input is x and the output is the label, that is your prediction, then the model that we train would be called f. Now, depending on what we want the y to be, F can be different. If we are classifying something, then for example, scenes. If you give an input to this image, then it would classify this as coast, this as forest. This is the same thing that Facebook would use when you upload a picture. It would find where the face is or who the face is, and it would classify. It would do a face classification on you when you're giving that as input. So that's basically giving it a binary label of whether there is or not, or what it is among a given n classes. Then the other problem that falls within the supervised learning category is something we call regression. So when we are classifying, we are basically saying there's a cat or not. But maybe something like measurement. Actually, if you want to train a machine learning system to actually do measurement or predict an actual scalar value for something, for example, given this single image, humans can very well tell us, humans can very well basically say that this chair is close to us, whereas the chair is far away from us, and we have some perception about our depth. And can we actually label each of these pixels with the actual depth value? That is something we'll call as regression, where you. So for the previous example that we saw, where we were trying to predict whether to give or not a loan, regression in the corresponding term would be to actually predict what exact amount of loan we want to give to that person. Or something like an age prediction. Can I give an input picture of one of you, and it can try to predict the exact age? So it would not classify whether you're a male or a female, but exactly predict what your age is. So that's the difference between classification and regression. So as I mentioned previously, unsupervised is the other case where you actually don't have label. And what you want, this is the pure learning case. Yes, please.
The difference between classification and regression is that regression has, like, instead of like the binary thing of classification, regression is more like you have many different groups. So does that mean that just means like your training set would be a lot bigger than your classification?
Right. So in a way, one of them could be seen as a subset of the other in a way that if you have infinite classes, then that would become regression in a way, because then you try to go to exact class. Whereas for classification, you're already just limiting your output to a certain number of classes. Whereas in regression, it's basically discrete versus continuous output that you're looking for.
There's an infinite number of things that it can be, but
in a bounded way, yes. So for example, for classification, you would predict whether it's 0 or 1. For regression, you would predict a scalar value between 0 and 1, so it could be anything. And you would convert that into, so for example, in this, the classification example, for the depth could be, if it's a classifier, then it would predict it's near or far as 2 labels. Whereas for depth, for regression, it would give you the exact measurement, it's 7.2 meters away. So that's the main difference. So unsupervised learning basically would be where you do not have label, and as I was saying, this is sort of a pure learning scenario where you're just given data, you're not given any other information, and you're told to take meaning out of it. So clustering is, so this should in a way exemplify what a simple system should do. Given that you have a 2-dimensional scatter plot of this kind of a data, most of us could actually separate this out into 3 different blocks. And we can identify this as 3 different classes within our space of representations. And can our system do that? Can we actually train a system to actually draw lines between these 3 different classes so that if there's a new circle there, it can actually predict where it is? Even though it has no inherent idea about what these represent, yet it can find out, differentiate between what it is or not. So both supervised and supervised, I try to explain you what both supervised and unsupervised is. They are not necessarily competing algorithms, but they are more complementary, that you cannot always use one or the other. For example, if you're looking at the scenario about driving on a road, is it about whether there is a So you can have an unsupervised algorithm to basically tell you there is something in front of you, like a road or something. But unless you actually give it a label, it will never say it's a road. But it can always try to find, it can try to identify what a road looks like and tell you this is class A. But that would, so if you actually wanted to try to differentiate and use it in a high-level fashion, supervised would be better. But for supervised, you need to have millions of data points for labeling. So what the ideal machine learning system or artificial intelligence system, at least like humans would be doing, we do a bit of both. We have a certain idea about a particular, let's say you go into a forest and you see a bird. You know what the bird looks like and you know it's a bird, but you don't exactly know what species of bird it is. But once you go back and you Google it and you know that, okay, this is the species, that's your label, then that becomes from unsupervised to supervised learning. So you can associate your label to what class that you have learned. So the previous part was unsupervised, where you had a certain knowledge base about what you learned, and then you associate labels, and that becomes your supervised learning. Semi-supervised learning sort of captures that phenomena in a way that you have labels for a certain number of classes or some small data points, but you don't have it for all. So the kind of example I would say is, let's say these are two different plots here, where you can clearly see a pattern where these are forming two patterns here, which are pretty which can be clustered in a way, but we have no idea about them. But if we can label red and blue to one of those data points, you can somehow create inference about all the other points. So let's say you were just given this data, and I gave you the label for one of the points. And if I ask you that one of the top points there, what is it? Is it red or blue? Most of us would go for red because we see patterns in this. And pattern recognition is another form of machine learning where we try to associate patterns and try to find labels for them. So we've been talking about classification. I've already given a high-level overview of how this works. We get the data pairs, we learn a model, and then when we get new data, we use that model to do a prediction. The earlier part is called the training phase. So whenever you go and study more machine learning on it, or any papers on that, you would always hear the term training and then testing. Training is when you collect all your data points and your data sets, and then so in the robot car or self-driving car, this would be the example of Google just moving around San Francisco for thousands and thousands of kilometers trying to collect data. So they try to learn they don't, day one, you just don't let the car go out. It's just same like a kid takes some time to learn. We would first try to collect some good data and learn and find what its behavior is. And we would use that behavior to train a model. And that is called the training phase. And once you are confident about your training and the model that you have trained, you basically use that model, and every time you get a new data, you try to do inference on it. So based on the features, as we said, of whether we would give a person a loan or not, this is something like in a mathematical way what your model should be learning. That's something that is greater than y. It's on top of this line and on top of this line. So it should have particular savings above a particular value, and it should have your income above a particular value. And this equation can very easily be represented in mathematical terms. So every time you get a new data point, what you do is you basically compare against this line and predict what it would be. For example, now you get these blue dots. So one of them would be green, should be predicted green, and another red based on the current model. This is under no assumption that your model is correct. This is only based on what you've currently seen. So it may be that this whole thing is red, but if you've never seen any more data, you would never be able to do it. This is the same as imagine you train a system on Earth, and then you actually go out and run a rover on Mars. You may not even expect certain things to happen because you've never seen that on Earth. Certain microgravity behaviors, you just don't expect them here. So how do you actually build systems to train that? That's one of the challenges I would want you to think about. Like a lot of the machine learning systems or the computer vision AI systems that right now we are seeing out there is trained on millions and millions of data. But that's not always the case. let's say you go to medical imaging or something in rare medical cases, you would probably have 1 in a million case. Now, how do you use concepts from machine learning and single or very small data points to actually solve those problems? That's a very active area of research in machine learning also. So right in the previous image you saw, we were creating basically a 2-frame classification. But in this, you can also have a single line, and this is the most fundamental machine learning algorithm where we use a linear classifier. And all the self-driving cars and all the things that you see actually that can be traced back, this is the very basic roots from where it starts. Building thousands of such linear classifiers and stacking them together actually builds your deep neural networks, which are being used to actually do very high-level intelligent tasks these days. But the idea is you collect these two different, and you come up with your simple equation, y equal to ax plus, your simple linear equation, basically, and then you do your prediction on that. So that would be, so this line here can be represented with your ax1 plus bx2 plus c, your more a simple linear equation. And if you give me enough data points, what I would do is basically for each of these, you can, so to understand how we would actually train this system in the mathematical way, for each of them, imagine x and y being your representation on these two axes. So for the previous problem, x1 and y1 would be your saving and your income. And for that, you would have your prediction that would be based on whether it's positive, -1, or +1. And if you stack a lot of these together and form a matrix out of that, you can basically then learn the weight vector. And your weight vector is basically capturing A1, P1, A2, P2. So using a lot of these A1, A2, P1, P2 for n times, what you do is actually come up with an optimal value of A and B that would represent this equation. And that would be your currently learned model. So based on your current data, you learn this model. And this is the equation for that. Is there any questions on this part? Because I think on how we are actually generating the weight vector. Yes?
Well, my question is, like, are there any set of data points where linear classification is not well in the sense? Because
yes. So the classic case, I don't have it here, but would be your XOR, the XOR example, where imagine you have red here and green here, and then you have a segment where you have red on top of, do you have chalk here? So imagine you have x's here. Now, how would you try to separate this with a single line? Yeah, but linear classification. So you would need to go into, either you could use a curve, as you said, but what happens with the curve is it starts to become more computationally expensive as you start to do square. So the solution for that is you can basically try to have this kind of a thing, where you stack two linear classifiers together. And rather than classifying it in one shot, if you do two-level classification, then you can basically have a classification again for the same thing. And because this thing, two linear classifiers can be parallelized together, that's how you can make it computationally more efficient. And when you have millions of such classes, this is very toy points. Now when you actually go out, your output, basically your output starts to have millions and millions of classes. Then if you want to write a polynomial equation, as you said, with a curve, then imagine solving optimization which has millions of parameters trying to solve for that equation. It would go exponentially bad. But what you can do is you can do parallel linear calculations on that, and that's exactly what builds up the neural net. And that's the same way your human brain functions. Each neuron in your brain is basically like a simple classifier, and you can think of it in that way. And you have stacks and stacks of these simple linear classifiers building up a huge network of neurons in your brain. And every time you get a signal on your brain, on a particular nerve cell, you basically have a response which will be either positive or negative. And you collect these responses together and and that's basically what comes out as intelligence and decisions. Yes?
Some how the lines are being generated, because I understand like you can decide the optimal weight from those.
Right. So I'm not sure if you guys are familiar with solving linear equations, but basically if you have n parameters and if you have n-1 equations, then you can solve the exact value of the coefficients for that. So it's basically just like solving a set of linear systems. So you can write 5 equations, and you have 5 data points, and you have 4 labels, ax plus b, y plus c, and then you basically just solve that set of linear systems. So yeah, and this could not just be a one-shot learning. There is a subset of machine learning that's called evolutionary learning, which are continuous learning, which is something more closer to what humans do. With every new image that you're seeing, with every new lecture that you're listening to, with everything that you're doing, you're basically learning and your brain is adapting. So this model that you've learned keeps adapting with each new data point that comes in. So let's say you had the previous one. Now this makes more sense to do with the new data point. And so in this way, you can start to learn better. But this is very limiting, as he already pointed out, like what if this would not be enough? In the previous example, like how do you define which is which? So when you get a new data points, how do you define which is better, literally? I mean, both of them could be good or bad. Both of them could be good or bad classification. So how do you define that your model is good? So that is something where we have support vector machine, and this is the most fundamental algorithm which is out there, and a very powerful algorithm which is still used pretty widely for any classification task. And the idea is that what you want to optimize for is if you have is having a maximum margin between that. So the idea is like if you have a very clear difference between your two classes, then that is a good classification, as opposed to something where certain points are in between and it's very dicey which class it belongs to. So a good classifier is something that creates a big margin between your two classes. And I would not go into the math behind how we actually optimize this. This falls within the convex optimization framework, which we do not, we won't go for the scope of this lecture, but like if you guys are interested, this is one of the most fundamental methods and yet powerful methods of solving most machine learning tasks. Yeah. So another algorithm that I would quickly try to cover is the nearest neighbor. This is another. In the previous algorithm, what we were trying to come up with was basically trying to maximize the margin. So we would, as we have millions of data points, what you would do is you would try to iterate over those data points and try to see which division basically creates the maximum margin between two classes, and that will be your most optimal classifier. In this one, what you do is you basically create, you iteratively keep creating classes, and as you get new data points, you start to see which one is your closest one. So either you can just see which is the nearest and classify it according to that one. So for that, the analogical example would be like if you have, basically if you've seen a lot of cats and then you see the picture of a lion for the first time, let's say, what is the closest thing you have seen to that? And you would try to basically say that is a cat. Or let's say you have seen 100 species of fishes, and then you get a new species of fish that you have never seen. And like, it looks somewhat different from all the others, but the closest thing you've seen is a fish. So this is what that captures, basically your nearest neighbors. And another iteration for that would be k nearest neighbors, basically, where you don't want to basically limit your system to be very biased towards one data point, but want to have a more compact. I would quickly try to cover one more algorithm on the unsupervised and then show you two application videos. For unsupervised case, as we just said, what what we're basically trying to look into is the idea of clustering. And that was sort of covered by the k-nearest neighbors, that how do you cluster together, just by looking at a lot of data, how do you cluster together things that look alike? For example, all these pictures in land. And even within the same species, this looks very different from this. A Siberian tiger looks very different from a tiger in Bengal, India, and stuff like that. All the species are different. So how do you manage to capture all the variability in how a particular animal looks like, yet differentiate it from another animal, and for that matter, any object? That's the problem of clustering. How do you reliably do clustering? Because similarity itself is very hard to define. How do you define? On a particular, in a context, you would define, you can say these things are similar because both are living organisms. So it really depends on what your problem is, and based on that, you have to define it. But when you're doing unsupervised learning, oftentimes you don't have that. So that is something to consider about. So the goal for clustering is given just the input data without any labels. How do you basically partition into k classes, and your k classes come from how fine-grained you want your output to be. Since we are running a bit out of time, I will skip some of this and basically try to show to how you guys can use this in some of the work you're doing, and what are some of the so one of the things we talked about was segmentation or classification. So if you guys are trying to build robot cars that would move on lanes, one of the things you can do with computer vision directly, and especially machine learning into it, would be classify where a road is or where your lane is, because trying to build a mathematical model to find where exactly what part of it is a lane is a very complex behavior that you will not be able to capture by just equations. And you would want your system to learn. So what you would, and this is an example of that, where what the video here is trying to do is basically, given a video where the self-driving car is running, it would try to just estimate based on geometry where the plane is. So you don't necessarily need to do this because this is more involved. But what you can, a simpler version for your robot car could be to think about is basically, if you have the region you're working, the image right in front of you would be also the road. You're not looking at something else because it's very close to you. You know as a prior it will be your road. So can you use a part of the image that you know will always be a road, and then extract features out of that? So I will try to show you this video first. So what it's doing is basically extracting features, and the blue is the features that we talked about earlier. It extracts these features out of it, so it knows where this is, and it uses that to train a support vector machine, basically, on the fly. And what it's trying to do is use that. So this is the features, basically. So you can use simple features as color histogram, as you mentioned already. So if you just extract the colors in front of your image, you create a histogram out of it, and you train a simple support vector machine, you can start to predict in the image which parts are road and which parts are not. And once you have this information, what you can do is you can actually, now your car knows where it can go and where it cannot go. So this cannot deal with a lot of other things that an actual self-driving car would need to do, like pedestrians, but those will be different algorithms for that. But one of the most prime things you would need to do is at least know where the road is, so that it doesn't start going over footpaths or start going into buildings. So the equivalent for you guys on this would be, can you identify the lanes you're moving on? And if you have a very good idea about the lane that you're moving on, what you can do is you can move really fast, and you can design a trajectory or a path where you want to go for that. So that would be one of the direct applications. Another application which I've also worked on previously during my thesis, and is something very interesting that I find, is a version of machine learning which I could not capture here in this talk, is something we call imitation learning. The idea in imitation learning, and actually what some of the first self-driving cars that were built use, and also a lot that we currently Google uses, is the idea of basically humans are great at doing piloting things. So human pilot can basically pilot a UAV, and we are good at driving. So can we make a driver drive a car for thousands and thousands of miles? we keep collecting data of what he's looking at as the image and what is the instruction he's giving to the car in terms of steer angle. So basically, looking at the image, can you try to predict whether to move left, whether to move right, and in what amount? If you can capture that simple mapping, then you can basically give that as a control command to your steering angle for your car. And basically, as your car moves, what you will do is you basically try to predict how much your steering should be moving left or right, and that would be your simplest way of driving. So this is what it's doing. It's been trained on a system to predict left or right steering angle. If you see on the left, and this is a regression. So what it's trying to do is basically trying to do regression on what angle it should be moving for the next few seconds. And this is, as I mentioned, is called imitation learning, where you're trying to basically imitate a human pilot or a human driver. So once it has got enough data, it's basically now it knows how to. So if it sees a particular scene, it knows where it has no idea about what a road is. It has no idea. Explicitly, it's not doing a classification. It's not trying to find where a road is, what a path is. It's a form of learning that we call end-to-end learning, where just looking at an image, you know whether to go right or left. And that's something humans also do. When you're actually driving, do you actually map every single pixel of what you're seeing? Do you really have exact measurement of this is 32.3 meters away and I should plan this polynomial trajectory? That's not how the human brain does it. What we do is we have a reactive control where we know how to react and what angles to provide to that. And this is something that we call reactive control. And we are doing end-to-end machine learning with it. So this is something which is a very interesting project also if you guys want to go out and further learn and experiment on. That could be useful. So as a finishing summary, just like some takeaway, I gave you some intro to machine learning, and how I would want you to look at machine learning as basically a tool. It's not the solution to computer vision. Machine learning, people who work on machine learning think it's a solution to computer vision. But vision thinks it doesn't. The people who work on computer vision think machine learning cannot solve our problem. And the thing to take out is that both computer vision and machine learning are very complementary things, and you really need to understand the pros and cons of each of them to use them together, because there are certain things about model-based computer vision that cannot be solved without learning from data. And data alone cannot solve a lot of problems, because there are certain concepts and priors about geometry and inherent that we need to understand. And the reason for that is that we do not have infinite data. The place where machine learning would be perfect is when you have infinite data, because then you have seen everything. If you've seen everything, you can always correlate it to something. But if you want to build systems that can handle with uncertain cases, then you want to have model-based systems for that. Okay, thank you guys. I hope that was a bit useful. And that's my email up there. If you guys need to contact me, any questions, anything, yes, please.
Practical applications of the algorithms, like which ones would have you most used, like at JPL?
That's an interesting question, actually, because at JPL, this is something I am facing every day right now, is the fact that in the community, you have such heavy algorithms and you have so much progress in deep learning and machine learning and those kinds of things, which require huge computation. But the problem is when you actually go down, when you think about putting it on things like the Mars rover, you have a huge issue because you have no computation, first of all. I mean, the rover that's currently moving on Mars is at least 1,000 times less powerful than your phone. So you have literally no computation, one. But there is a bigger reason that is the problem, and that's robustness. Most of the machine learning or computer vision technology, it works great, but it doesn't work perfect. It's far from perfect. But you cannot build a $5 billion robot and send it to Mars and then say, oh, we failed because this did not work. Because of one out of a million cases did not work. that's very so the thing so when we are now designing algorithms at JPL is you really look at simple things that work great. You don't try to solve all the problems, and you don't try to solve the general problem of AI, but what you try to come is if you exactly know what problem you need to solve, you can really design your algorithm in a very simple fashion for that. So there's this two stream of computer vision. A lot of research people, what you're trying to do would be to try to solve more general computer vision, so that can work in a lot of scenarios. But if you have a particular task, for example, if you're trying to build self-driving cars for the road, you don't care about forest environments. You're not going to go off-terrain. There are other people who are for the military trying to build things that would work in off-terrain. But so if you know your environments, you can set a strong priors. So that's something to consider.
Specifically for the task that you do.
Exactly. For example, as I mentioned, SVM. Let's say you want to put something on your robot car, and actually, or even a small robot car. It would have a very small computer. You would not have, first of all, the data or the time to collect millions of data points. Second, most of your heavy algorithms would not really work because you don't have any space. You can put a big computer on your car, but you cannot put it on a small race car or a flying robot. So then you start to think, then SVM is actually a very powerful robot that people, very powerful algorithm that people still use for most of those tasks. So it really depends on what you're trying to use and how. So I don't think I have a straight answer to that. Yes.
With when you're talking about like the evolutionary data like sorting and all that, I was wondering. So like you say like a lot of times in the world like there's things you don't expect to account for. Is there any way to like have it in your code where like you can account for like say an entirely new topic? Like we're going back to like let's say back to like that whether you get along or you get along. What if like they create like this new category where it's like people that get like this special one, like they're squares now instead of X's and O's.
Right.
How can you make a code like account for them in group, or is it just gonna sort them to X's and O's?
Yeah, I think that's a very good question, and that's a very active area of research right now. And how do you identify these unique? And it sort of falls into the category of like anomaly detection, like because that's anomaly. It's not really a noise, because it makes something, it has a constituent class, it defines something factual that we want to know, but the problem is according to everything else, it's a noise. So how do you identify that? And there's some work on it, but there's still not a really great algorithms that work amazingly out of the box for that. But there's this, if you want to go back and study more on it, this falls within the class of zero-shot learning. So basically the idea is you should be able to classify it the first time you see it. And so that's another thing that you can go back and read up on. Yes?
So you said with imitation learning, you base it off of like what you used to drive or how they would drive. Mm-hmm. So how would you deal with like unexpected situations like collisions? Because a human doesn't always handle that properly.
That's again a really interesting question, and so just a background, like I was working on imitation learning during my master thesis like last year, and what we were trying to do is basically use imitation learning to avoid obstacles in forest. And one of the main problems for that is in order to learn that behavior, you actually need to crash into obstacles. So if you're actually building an expensive robot, in order to train an imitation learning system, you actually need to go crash your system, so that it understands what crashes is versus what crashes are not. So that's a fundamental problem. One of the ways to get around that problem is what people are now trying to do is use simulation. Since if you can do that in simulation, and you can transfer that knowledge from simulation to actual. So basically for the video that I showed you, you can crash as many times as you want while you're playing. So there was a recent work where what they tried to do was play GTA. So they made people just play GTA for hours and hours and days and weeks and learn that behavior to actually put it on a car. So something like that. So you have to get around the problem sometimes because you can't directly solve it. Thank you.
Thank you so much.
Thank you so much, guys. Glad to be here.
Yeah.